Thank you, Sean. I use my mother as the standard for introducing me, and Sean comes a close second. Is what he said. Okay? My mom would have used something more, but thank you for the opportunity to come to New York City. It looks like great weather, and the U.S. president followed me, so which is not a bad thing to brag about. So I'm going to do. I talked to some of you already, so I kind of get an understanding of, where your interest lies. And my job today is to kind of not tell you everything, but tell a little bit about who we are and what we do, about U.S. National Laboratory System, which is mostly known for our nuclear mission. So there is always a question about why are we doing geography or geospatial science. So I need to explain that. I'm going to run through a few highlights in the themes around, how we use geographical and geospatial science for touching 4 different things. One is I'll talk about, how we are using AI and large computing for creating new data resources, show some examples of analytics, give you a flavor for something that we get to participate every day, which is supporting the mission, the federal mission, and it will become obvious about what we do. And I'll use Ukraine as an example. And then I have one example of how we try to translate our science and technology into more practical spaces, like how a city would embrace. And then at the very end, I also want to show you a couple of examples of, why do people come to Oak Ridge National Lab or any national lab, and why do they stick there? So somebody asked me this question before, that how did you this place get to Oak Ridge, right? So there is no secret that the Manhattan Project, which I'm assuming that some of you may have heard about, where these 3 locations in the nation were picked to create the capability for having a nuclear explosion, the atom bomb. And that was prompted by a letter to President Roosevelt from Albert Einstein that said, this is possible. So Oak Ridge was one of those sites picked for its geography. It was well hidden, away from the coast, and very little population to be moved. Okay, and there are some interesting stories, but essentially this Clinton pile, that's what it is to be called at that time, became the longest running continuously operated nuclear reactor in the world. There were 3 sites in Oak Ridge. One is what is Oak Ridge National Laboratory today, is to be called X10. That's where plutonium enrichment using a graphite reactor was being pursued. There was another site called K25 that was doing chemical separations, and Y12 was using another process. So there were investment to, do 3 parallel tracks of plutonium enrichment, not knowing which one will become successful first. And Clinton pile was the first one to go critical. So this is part of a national park system now. This is, if you go to the National Park website, you will see Manhattan Project National Park. And this building that is about 300 yards from where my office is. My office, when it was about 150 yards from the graphite reactor, it took me 9 years to actually go and see. Okay, so there is an inverse relationship to your distance about how important do you think something is. When it's right next door, you don't think you should go, right? But this is a place where the beginning of the changing of human history. So I mentioned the 3 sites, right? And these are amazing maps that shows how geography was used to select these sites for a variety of. So in today's GIS, you are always doing this site selection, right? You throw in some criteria and you say, where should I site this particular facility? So a very similar exercise was run at that time without having GIS as a commercial software. So it was significant amount of data contributions that came. I was fascinated when I got to Oak Ridge looking at this map. there are two things to look at this map and kind of understand. The history. The first odd thing about this map is it has a tilted north arrow. Okay. And to every geography student, that's like a seminal mistake, like a fatal mistake that you can never make. Everybody teaches you the north arrow is always to the top, right? So that's a confusing thing. The other interesting thing is there's black marks in there. And if you look very closely, you will see that what that says is that it was declassified on 6/11/1958. So this map was actually a secret document because that's where all these operations were going on, right? So originally, and this is one of the old lithographic maps that I found at the lab, and there is a name of a person inscribed at the bottom left corner who created this map to scale. And then you can see the true north versus the Oak Ridge north. So what I found out is the history was that there were a group of mathematicians, and essentially these are photogrammetrists who were brought together to create this Oak Ridge projection system. So the three sites on Oak Ridge, K12, X10, and K25, they all had their own projection system. So all the maps were made using that projection system. So by any chance, if that got leaked out and you did not know the conversion, you could not tell what the original lat longs are on this map. Okay. So I had a colleague, Phil Coleman, who wrote this famous software called TORC, Transformation of Oak Ridge Coordinates. And if you did not know that, you could not ever decipher where the things were. So today we are, the National Lab System. There are 17 of them. They're all part of Department of Energy's mission. There are a group of labs that serve the science mission of Department of Energy, and of which there are few large multi-purpose science labs: Lawrence Berkeley, Pacific Northwest, Argonne, Brookhaven, and Oak Ridge. And Oak Ridge is the largest multi-purpose science lab. Then we have nuclear-focused labs, energy-focused labs, National Renewable Energy Lab in Golden, Colorado, Idaho National Lab, which is focused on nuclear, and National Energy Technology Lab in Morgantown, West Virginia, that's focused on fossil fuels. Okay. And then there are three ugly sisters. These are Lawrence Livermore, Sandia National Lab and Los Alamos National Lab in New Mexico. These three very large labs, they support the nuclear mission of the department and the nation. Okay. So they are about 3 times the size of Oak Ridge. So we are about 6,000 people. Los Alamos has about 15,000 people, and Livermore and Sandia has even more. And then Savannah River National Lab is it used to be a user facility. Now it has become an environmental focused research lab. So this is what it looks like, okay? It's beautiful. We are 40,000 acres. When summer students show up, they get a shock that the distance from the last traffic light to our building is about 6 miles, okay? Before you ever get to see anything. 40,000 acres. We have 6,000 people and 80 megawatts of power coming in, part of which is because of the large computers that sit there in there, and 10,000 deer. Okay, so I don't want to ignore the deer. So there's plenty of them, and turkeys. So national labs in general, we do projects at scale that make the needle move significantly in our history. So some of the things that I found fascinating is this is where nuclear medicine originated. Okay, so today cancer treatment, which is radiation, that came out of Oak Ridge because of nuclear radiation measurements on mice. We produce about 30% of the medical isotopes of the country. So there's a new isotopes that go into medical treatments as well as providing power to the Mars Pathfinder that runs on that surface, okay? The fact that the Y chromosome, the presence of the Y chromosomes leads to the male gender was discovered in mice at Oak Ridge. Okay? So it's amazing history of what it is. And then sometimes people end up discovering a new element. So tennessine is then one of the newest elements that's on the periodic table that was discovered at the lab. So it's a very impactful place to be at. Okay. So the organization that I belong to, Geospatial Science and Human Security, we have these research focus areas: high performance geocomputation, human dynamics modeling and simulation, critical infrastructure resilience, remote sensing and autonomous systems, and then geo AI for mapping and monitoring. So I'll touch a little bit on these things. But the areas that we are really trying to make a difference is situational awareness, time to decisions, how fast can you do something to support decisions, crisis management, and then energy and climate resiliency. What we really do well is provide information and describe these 4 different landscapes: the human landscapes, the built landscape, the built environment, the physical landscape, and then the information landscape. Okay. And as you hear me speak about different things that we do, you will recognize that at the foundational level, these are the 4 elements and pillars that we are following. So we are about 100 scientists and researchers in the division that are core with geospatial science. We are also the largest computing complex in the world. Okay, so we have the #1 machine in the world that is 3 floors down from me, called Frontier. The #8 machine in the world, which used to be the #1, called Summit. This machine that you are seeing is Air Force's machine that does their weather and climate calculations. We have NOAA's largest machine called Gaia, that is also 2 floors down from me. So in the building I am, there are about 30 megawatts of power comes in to power these supercomputers, which will light up quite a few cities. And some of the things that we are doing is, trying to understand how this geographic data and these large computers allow us to do, support missions in disasters and response. And one of the things, much better than what we can do otherwise. So I'll talk about 2 things on this AI. One is, I'm trying to mute this. So settlements and population. This is something that we have done very successfully for the last 25 years or so. And we are very well known in the world for creating these data sets that everybody around uses and supports decisions every day. So we have a model called Landscan Global that resolves at 1 kilometer, about 30 arc-second resolution for the whole world. So we describe every year how many people are for every roughly 1 kilometer cell. Then we have a model called Landscan USA that describes nighttime and daytime for the US 50 states in 90-meter resolution. Okay, and that's a bottom-up and top-down. And then we also look at these simulations of dynamics. So this is Washington on a 24-hour diurnal cycle of how people come in and go, right? So what you're looking at is not just dynamics of people, but you can think of that as your energy demand map, because people drive energy demand. Where we live, where we work, and how we go back and forth is essentially what defines how much energy we need. So knowing where people are at different times, helps us understand calculating building, from energy at building level to residential level. And since mid-2000s, we have been trying to see whether we can scale the US model to the rest of the world. Okay, the first part is to get to a 90-meter resolution global population distribution. And then we will look at daytime and nighttime, which is much harder once you leave the US or in Western Europe, where you don't have that much data. So how do we do it, right? So there must be some kind of a magic. So we use a very simple logic and principle that if I know where every building is on this planet, I know where humans are active. Okay, they don't grow in nature, and nobody builds, a structure unless there is some kind of an use for it, right? Although you would debate the Chinese are building lots of structures where there's nobody there, just large, big structures. So at the very first level, we are saying that the US government spends $350 million a year collecting high resolution, 30 centimeter resolution satellite image for the whole planet. What can we do with it? So what we are saying, and we can understand where settlements are and where buildings are, and we are going to map every building in the planet, on the planet. From those buildings, we derive a second level machine learning model that allows us to understand neighborhoods. And what neighborhood means is that these are kind of homogeneous structures that defines different kinds of clusters in that. And so on one end are what I would call extreme informal or slums. The other end is like Manhattan, where you have very, very structured, large, well-defined structures, okay, buildings. Then we do few different things. One is we try to understand how tall the buildings are. We try to understand what those buildings are used for, okay? And then we also try to understand what kind of population density can you expect for each of these different areas. And all those things get combined into ultimately creating the final output of, how many people are at that resolution. Now I'm simplifying it to, the deepest end. Each of these bubbles are multi-million-dollar projects every year. Okay, there's a large group of people working. So I'm going to break down a few of these things to give you a little more examples of it. So why is this a challenge? Okay, why do you need large machines and a lot of data and a lot of effort? Okay, so 2% of the world's surface, land surface, is occupied by buildings. 2. Okay. So here's a couple of examples, Mali and Venezuela. In Mali, 0.02% of Mali's area is a building or a structure. And in Venezuela, it's 0.13%. So when you are looking for these structures in satellite images, this is a needle in a haystack problem. Okay. So it's not that easy to make these things work. So we invested in a couple of different things. One is first is, create AI models or AI ML models that can identify buildings in a satellite image. Okay, so that's the first part. And we got better and better and better in defining those models. The second part is how to get very large machines to help make that mapping work. Okay, so here is an example. Summit, which is now the number 8 machine, which used to be number 1 a couple of years back. You can use these GPUs very, very smartly to scale your mapping exercise. And the benchmarks are that you can use the 3200 GPUs that are on that large machine and map every building in Iraq in 4 minutes. Okay. Titan used to be another machine that used to sit, that was number 1 of several years back. We ran a benchmark there where we used 5,000 GPUs on that big, large machine and mapped every building in Yemen in 1 hour and 41 minutes. And this was previous generation, right? So with fast, bigger computers, this mapping becomes a very, very efficient and quick process. So here is Caracas, Venezuela. This is a satellite images of 30 centimeter satellite image. These are all the buildings from Caracas, okay? And then when you do that second order machine learning to say, what are my different kinds of neighborhoods, you start understanding where industrial, commercial, informal slums, formal, residential, formal. So you can generate it in different ways. And we are having very, very good luck in deriving it from data and also deriving it with real experience of where we would go and say, okay, I'm going to train my model for doing this. But what we are finding that when you have lots of these buildings data, the geometries and the spatial context actually allows you to create a machine learning model that predicts land cover or land use very efficiently. And you can do this like for billions of buildings, absolutely super fast using these things. So there are lots of spatial clues that are included in these things, right? So why are we interested in this? Because these formalities are connected to your energy demand and energy use. Okay. The more formal the structures and the buildings are, the more energy intensive those buildings are likely to be. Okay. If you go to the edges of these cities where you have these informal settlements, refugee camps, there is a very little energy that's going in there, right? So the demand, so you can kind of understand the changing landscape. And I'm showing you a one-time snapshot, right? When you start doing this over time, you also understand how these urban areas are evolving in terms of which kinds of neighborhoods are growing, where are they growing. So in South America, we found that even the country governments have no good understanding of where, especially in Brazil and Venezuela, the favelas, which they are, the informal settlements, they have no idea how much they have and where they are. So I had a PhD student several years back who was working, and he was, I don't want to bore you with the equation. There's a few papers on this. And his question was, can I validate it, that what I just said, my energy demand, by just looking at the correlation between nighttime lights and these different kinds of neighborhoods? And it is not like 90% correlated, but the correlation is fairly strong. So there is some validation of how well these work. So anywhere between 6 R squares from 6.1 to 6.3, but then you get Johannesburg, which didn't really work as well as we had expected. So I don't know how many of you know that, but we were the first entity to map every building in the US, although New York Times ended up publishing the Microsoft version. We actually have done this twice. First one from an imagery set called NAPE, National Agricultural Imagery Program. That's an aerial image at 1 meter resolution. And the reason that NAPE was really well for a generic AI model was because the images are balanced. So people go and balance those images, so more consistent imagery. But now we have completed mapping the entire nation with high resolution Maxar. This is the world view images for every building. Okay. And then now we are characterizing those buildings in terms of their building use. So 125 million or 125 million plus structures that are 450 square feet or larger. Now you can ask me this question saying, how did you get 450 square feet, right? What made that number stick? I'll give you that secret. 450 square feet is the size of an average mobile home. Okay. So when we first got tasked by FEMA to do this, the nation did not have a comprehensive map of where our mobile home parks are. And that's called the tornado magnets, because the slightest of winds or flood, those are the ones that are going to get washed away, right? So that's how the 450 square feet came. And now it's, so you can go and access that data, whole data. It's in the public domain from FEMA's Geo platform. So you can go and pull in the entire nation. But this was our first experiment in processing, 74 trillion pixels was how much we had to process using these big machines. So, you're getting the hint, right? So, these machine learning models are good at object detection. So we helped the Department of Energy about 10 plus years back, developing an algorithm that detected solar panels. The question is, why do you want to know where solar panels are, right? The reason is that who has solar panels is not a public information, okay? And the market, the companies who do installs, their last mile is really hindered by their lack of knowledge of where should they go and do this, right? So DOE created these kinds of a data set to make it available for them so they can do targeted marketing. So if a neighborhood is seeing a few people putting in, you're more likely to be successful in market penetration because you know that there are people who are, everybody does a follow to the Joneses model, right? All your neighbors start buying a 85-inch TV, you are more likely to buy an 85-inch TV, right? That's how we work. The other aspect is, it also gave us an opportunity to understand from underlying socioeconomic data, who is adopting that technology. So you can go and target those demographic groups elsewhere in the country, right? So that was the other. So this was a thing. Taylor Hauser, one of our researchers, he came up with another cool application. FEMA came and asked us if it was possible to map very small water bodies after one of the hurricanes that hit Puerto Rico. And because these waters get, stay in people's backyards, small areas with the surge, and then they become mosquito breeding grounds. And we were very concerned about Zika, okay? So Taylor took a very simple NDWI approach on this worldview imagery and scaled it to 4,000 nodes on this Titan supercomputer and mapped every small water body in the state of Texas in 10 minutes. And on top of that, he was also able to come up with an index that showed how clean that water was, which means, how much static that water might be, right? It's a very simple application, but it's a very powerful application, so you can create. So now we are looking at scaling this to the whole world. We are pursuing a concept called Hydroscan, which is essentially a global inventory of water. You want to know, because the biggest thing that is going to impact us is water, right? Climate is the driver, but the resource is water, right? Is the most artificially costed commodity we use. If you truly cost water, none of us will be able to afford it. Okay? So it's a most artificially, but it's a very, very important resource for us to understand where water is. Here's the other application that we did, which is understanding where mass graves are. So right now, there are a lot that are being discovered in Ukraine and Russia. And these things come and go very fast. There was a graduate student at University of Tennessee, which has a very strong forensic anthropology program. I was on her committee. She actually did this experiment where she took a control site, which was a fake grave, and next to it was a real grave. So she found dead bodies that gets donated, or they find it, unclaimed. She put it on a grave and created a sort of a mass grave thing. And then NGA flew their satellites to see. It is amazing how fast you cannot tell between the two. And the other thing I learned, that the grass does grow greener and faster on where the body is. I also found out that large utilities actually use remote sensing to understand septic tank leaks from the exact same way. That all of a sudden vegetation starts growing quicker and greener on wherever that sewage is coming up into the ground. Okay? Cincinnati water, they do that routinely. So this is very important. So the other thing I wanted to point out is that the numbers you're seeing here, this is a human counting the number of graves versus the machine giving you a prediction, right? And they're dangerously close to each other, right? So we are getting it to a state where it's very, very close, so which is very encouraging. And here's another example of, manually machines don't get tired. We were having these conversations, right? So when you have to do this, humans get tired. And if you put 3 different people to count, they will come up with 3 different answers. And we have done that experiment as well. So very, very high. Here's another example of how do you take lots of data, large compute, and create something that is useful for a lot of different reasons. So all of you know about elevation data, right? Fair? Okay, so one way of generating elevation data is active remote sensing, that you use something called radar or LiDAR, and you create remote sensing data. So the SRTM, the Shuttle Radar Topography Mission from NASA, that created the 30-meter resolution global coverage that most people use. So when this problem was brought to us, that SRTM is 30 meters, SRTM mission took many years and lots of money to create, what could be another alternative for generating very high resolution elevation? So we took a slightly different approach, which is we basically said, well, the government buys $350 billion worth of satellite images, 30 centimeter satellite images, or a meter or half a meter every year. And it sits in an archive, right? So you have this massive archive of images. So maybe there are image pairs of the same area that will give us a stereo, right? And if we can exploit that stereo angle, then we can create a 3D point cloud from that stereo thing, right? This is the exact same principle that Polar Geospatial Center, which is funded by NSF, is using for mapping and creating the Arctic dam, the Arctic and Antarctic dam, right? The reason it's easy in the polar area, because most of our satellites are pole orbital, right? So they have the maximum coverage on the pole. They're always passing through. So you have the maximum number of things. So what we did is we took that algorithm, we fine-tuned it on high-resolution satellite images, and then we custom designed a chipset to build about a 3 petaflop machine or 10 petaflop machine that sits at Oak Ridge and then processes these images, right? So I want you to closely watch. This is the background is SRTM, and this is the output that is coming out of that stereo image processing at anywhere between 2 meter to 1 meter resolution. Okay. So University of Alaska Fairbanks is actually processing. We have set them up for this unclassified data processing. And we are doing it on a totally different data set that is not in the public domain, that I cannot talk about here. But these kinds of data sets will come soon available. And I already talked about it. So I don't want you to read all these things because then it gets distracting. So here's what it is, right? Originally, when we started this project about 3 years back or 2.5 years back, one of the things that we were worrying about is that, okay, how do we know where to go and update elevation? And everybody said, oh, we need to have a change detection algorithm that will understand change, and then we will go process imagery and get a new DEM. Well, right now, the speed we are doing this on that big machine, we can create a global coverage in less than 9 months. Okay, so every year we can have a global coverage, and it's linearly scalable, right? So if you put a bigger machine, we can crunch it down to like 4 months. So every 4 months, you can get a totally new skin. So the change detection becomes irrelevant. In fact, now you can detect change from elevation because you just have a new skin, right? So it's almost like, when you go take a television that your TV is not working and you call the person, the expert, and they said, well, it's going to take you $500 to fix. And you say, well, I can buy the same TV for $300. Why do I want to ever fix it, right? I'm just going to buy a new one. So it's sort of going into that kind of a domain. So this is very, very exciting. Let me talk a little bit about what we do for analysis and supporting analysis at different levels. So this is an informatics project, okay? So this you will appreciate. We designed a system back in 2003 after that massive blackout, and some of you may be too young to remember that massive blackout, but there was a massive grid failure and blackout in 2003. Which prompted the whole United States and the utilities to have this urgent need for wide area visualization. Do I know what's going on in the nation, right? So we created this capability by aggregating data from the utilities. It was for some time, it was at DOE, and in 2016, DOE pushed it back to us saying, you guys need to run this because it's getting too complicated. And even Esri failed in making it happen, okay? I will not tell them that, but they did fail, okay? So we took it over. It is built all on open source software. And the simplest way to think about it, this is called Eagle Eye, and you can Google and see what Eagle Eye is. This is a system that it's a portal that looks like one on the left. It shows every 15 minutes how many people in the nation are without electricity. So it's near real time, 15-minute lag. So we are harvesting data from the utilities through a variety of mechanisms. Some directly report it, some we scrape the web, some have some mechanisms of aggregating it through the state. It's a very complex process. And about 3,000 utilities are out there, right? So it's a big effort. And then it's every 15 minutes, it gets updated in terms of how many people are. And then you'll see these trends, whether it's going down, what's happening. This runs 24/7, 365 with a 99% availability. Okay. So the amount of, and this is where I can never overemphasize the incredible work that geoinformatics engineering group does, is this is what Google measures its performance with. Okay. If you did not know, you should know that Google's measure of metric success is that if you are anywhere in the world and you in a browser, you type google.com, how many seconds will you get a 404 return? That it will not return the Google thing. That's their measure, right? That reliability. 90% plus, every percentage point is annually about $1 million that you need to devote towards to get to that next 1%. So it is very, very important. Okay. So we have active users from DOE and other federal agencies. I found out the hard way, all the places it runs, that includes the White House Situation Room. Okay. I was sitting in my house. I suddenly get a text from my deputy lab director, our COO, saying, what's going on with Eagle Eye? Because I just got pinged by the White House. The president was giving the State of the Union address. And since Tuesday was a good day, our people, IT people, decided to push a system upgrade and update, which took the system down. And it immediately prompted in a call saying, what is going on? Why is this system going down? So we know not to do it without, it was another research project. But this is what goes to the White House for declaring presidential emergencies. This is the data that the Secretary of Energy takes to the White House. Okay. I'm not making this up. Here's another example of what we are doing with this ESF12 community. After any major storm or any disaster, the first thing that you need back is energy, electricity. Okay, so FEMA has these 15 emergency support functions, 1 through 15. Number 12 is energy, and that's what DOE is responsible for. So anytime there is something, DOE will deploy the regional coordinators who will go and help coordinate the restoration of the grid so people can have power back. If you cannot have power back, you cannot pump gas, you cannot do anything, right? So first is generators, the Army Corps of Engineers, and then the DOE people along with the utilities going and fixing the grid. The biggest challenge is that they have to wait till the wind dies to 20 miles per hour, okay, for safe operations. Then they cannot drive their pickup trucks because there are fallen trees, fallen debris, flooded streets, right? So you have to wait for all these times to do it. So what we did is we essentially took a very elegant AI model that is very efficient in recognizing, identifying a utility pole. So it is embedded on this drone. The drone flies, it's in real time, it identifies which pole it's looking at because it knows the coordinate. And then it does a very traffic light signal, right? Is it still standing? Is it fallen? Or I cannot tell whether it's fallen or not. And it takes that small package of information and passes it through satellite comms back to the base, okay? Because you do not, remember, you do not have cell coverage, right? There is no Wi-Fi, there is no cell. Cell towers are down as well. So it uses satellite comms, and that's one of the technologies that one of the groups in my division does, is the resilient comms. They come up with this resilient communication technology. So it smartly finds out what is my channel that I can use right now and pushes data, okay? So we ran this thing, in the recent Mississippi tornadoes, and it is amazing how fast you can generate information. It comes to the people, and they can immediately start planning about how they're going to, start restoring the thing. What is down? How many poles do I need? Is the substation, under a pole? It's just really crunching that data to decisions timeframe. All right, so let me talk about a little bit of mission support. So all of you know about the crisis we are doing in Ukraine, right? So what are some of the things that we needed to do? Here is another communications and sensor technology, right? So instead of a drone, what we did is we were asked to create these boxes that has this variety of sensors, a solar powered battery, because all the IAEA inspectors had to leave Ukraine, okay? The biggest threat was two things. One is Russia doing anything for, damaging one of these 7 or 8 nuclear power plants that could cause a massive disaster, okay? Or is anything else that is going on. So the only way you could do it without having is to have somebody passively sense the radiation measurements around the sites and then telemeter data out. So this is also something that runs real time at the lab and at DOE, where they have those images, they know where these things are, and they get a reading in near real time. Again, using that satellite communications, right? So there are two reasons it's also used in the government for verification and validation. So President Zelensky is always saying that the US needs to give us so much money because we are in trouble, this is happening. This is another way of validating, saying, is this true? Is there that much damage that we need to be worrying about? And those readings help us explain that if the damage was that severe, we should see some elevated levels of, radiation in there. They had to build 6 of these things in 2 weeks, and actually it was handed over to the Polish who took it to the border and put it there. And then right now they're building more for other areas. So this part is all informatics and integrating that data into this interface. We did a nighttime light change detection very, very quickly, doing a differencing between the data streams on entire Ukraine, because lights are a good proxy for where you have energy and where you don't. And sometimes it's not the electric grid, sometimes it's generators, but you can also tell which one is coming from the grid and which one is coming from the generator, because it goes up and down. So this is another example of informatics working for this. The last thing is assessing building damage, right? Very, very quickly we had to understand where building damage is. One interesting thing was that we realized for most of Mariupol, the latest imagery was 2019, because we never thought that we needed to know anything more about the Ukraine, right? So 2019 was the baseline. And then we identified all the buildings that are destroyed, because every time the building model fails, that means there was a building that is no longer there, right? So that's the differencing you're doing. And that gets added up to our population model. So we were able to deliver a new, improved, high-resolution Ukraine population model for the government. In fact, Carter Christopher, who leads our hemodynamics section, was on a call with the people from Pentagon with Ukrainian ministers. And they did a check real time going to the Landscan portal. And their first thing was, how did you guys know? Because I live in this neighborhood and I'm looking and it looks pretty good, right? So that's a field validation. That's an amazing thing that how your science and technology is really making a difference. Okay, partnering with the community. So we do amazing things, but does it make a difference? So this is my one of my key urban examples and one of my most satisfying projects that I've been part of recently. So all of you know about LiDAR, right? LiDAR, and New York City has LiDAR. And then this is another example that you have seen that what is my solar potential for the buildings? So the city of Knoxville asked us about 8 to 9 years back now, saying, if we took all the buildings that the city owns, how much energy can we generate? So you run these kinds of analysis that this is a day in July that shows how the sun moves, and this is the place of worship, right? You guys know about this? The largest college stadium, Neyland Stadium, 110,000 people. This is, do not ever say that sports is played there when you're in Knoxville. This is the place of worship. On Saturdays and in fall, people go worship there. So we did this, right? So the next thing that came to my mind that I started working with a few people is saying, okay, we have all these roads and we are in this topography where you have this elevation, right? So you have ridges and then the valleys. And what happens is that the city of Knoxville has $140,000. They have a very limited amount of streets that they can de-ice. And it would last them about 2 storm events. And after that, they beg, borrow, and steal from other places and make it happen. Okay? 90% of the US counties which get snow break their budget from winter storm events. It's that severe, right? It's billions of dollars of money. So we did this simple logic saying, okay, I'm going to use the LiDAR data and I will see where the sun radiates more on the streets. Okay. So if one stretch of the road gets more sun than the other, then why am I going to put more salt on there? So right now, the engineering, right? So greater DC has 200 salt and brine trucks. I don't know about New York, but DC, I know about 200. Knoxville has 23. Atlanta has 2. For obvious reasons, right? So what they do is they have this salt and brine, and then the driver starts driving on the road. And if he's driving, the valve is open, it's spreading. And the moment he hits the brake, it stops. That's it. Okay. So we said, okay, why don't we create a risk map based upon slope and the shadiness of these segments in every 25 meters or so. And then we will create a controlling valve. And this is where the national lab becomes heaven. Because the moment you have an idea, you can find your engineering colleagues who come in and say, oh, this is a good idea, then we build, right? Then we partnered with the University of Tennessee, a business class, a class in marketing. And they executed this project with somebody's dad's truck and $1,500 for a field experiment. We did the lab experiment in a lab where we said, okay, can I move the geolocation and will the valves change, the spread rate? And then these kids basically got an old truck from somebody's dad, bought a big tank, filled it with water, put the valves, the engineering on there, and programmed it on an iPad and demonstrated it. So now, city of Knoxville has one, county has one, and I want you to watch this. This is probably my greatest pleasure of my recent last 10 years. So, this is what it says, that this is so grave danger. If you think about the property loss, is huge, right? Cars and, everything that gets. So this is the mechanism. Okay, it's very simple. That's spreading brown. That's the city struck, and you can see that it's running through the neighborhood. And as it's going, it's programmed on an iPad, and as it moves through the streets, it essentially knows how much to put in there. And you can stretch that amount of salt and brine you have so much further. Or by reducing the spread rate, you are minimizing environmental degradation. The street salt is the cause for, #1 cause for fish cancer. And the biggest cause for deaths in the northern half of the US, because that's where the deer come, right? Because the #1 addiction of the animal kingdom is salt. Animals will find salt, including us. That's how the elephants are motivated. That's how the deer is motivated. That's why people keep the salt pits in their backyard, so they can attract the animals and watch them, right? So the deer come in to lick that salt, and then we hit them, and people die. So right now we are talking to a variety of, including DHS, about scaling this, because it's simple scaling. You can take it anywhere. We have all the LiDAR data, all the streets data, and we can scale it very, very effectively and easily. All right, so I'm on the very end. So I was talking to a group of people recently who are new to the lab, just like, some of you who I just talked to today. And they said, well, you have been there for 25 years, so you must have had good times and bad times, and you have never left. And I said, that's true. I came for 2 years, and I'm aiming to leave in 2 years, but I'm just failing to do it. So there must be something that I'm enjoying here, right? So somebody said that, what were this great times, moments of your satisfaction, or you felt this was great? I gave a very bad answer at the time. And I went back and I thought that I did not have. And so I went back to her and I said, twice in my life, I've had this experience, which I would say makes it all worth. Okay. So these dots are the mobile home parks that we produce the data for the mission, right? We helped FEMA in one morning with a phone call. Chris Vaughn, he was the FEMA response director at that time. And I think this was Matthew or which one was it? Matthew, yeah, Hurricane Matthew. And the thing was, if Matthew comes, how many mobile home parks are going to be? So they said, we need this map. It's very urgent. So we helped them create that map. The next morning, this is another one of those things. So the next morning, Chris sent an email with this picture saying, you guys did great. Okay. It's a good day. I had another one in my career, which is our buildings data. The FEMA administrator talking to the president. This was after the Kentucky tornadoes. And that's what he's basing the decisions on, right? It's a great day. Okay. You can't take me away from this. It's an amazing. So Amy was talking about mission support, right? There's no bigger gratification of mission support than when you realize the difference you are making. So I hope all of you realize that I carefully use the word we, because I do nothing. Okay. It's a fantastic group of people that I'm surrounded by who do all this work, and they're amazing. And I get to talk about it at different forums and take credit for it. Okay. So thank you.